Hello, Science 30s. Welcome back. Hope you guys had a good break. I want to just take some time to talk about astronomy. This is the last section in the physics unit, and there's really no formulas with this one. All you'll need to know are the principles behind it. So if you follow through these notes, I'll do a few examples. I think you'll be ready to go. So, astronomy, yes, it's the science of objects and phenomena that originate outside the Earth's atmosphere, basically everything outside of Earth. I think you're all familiar with constellations. As fascinating as those are, you just need to know in general that's a grouping of stars. But what is a star? And that's what we're going to get into a little bit. Basically, a star is the product of nuclear fusion. What's happening is, and we'll learn this in the evolution of a star, is that gravity will start to pull mass together. And it usually starts in a nebula. So that's just a grouping of gas and dust that's out in the universe. And over time, of course, millions of years, sometimes, gravity will start to pull that mass together. And if enough mass gets pulled together and that attraction is strong enough, then this happens right here. This is the fusion reaction right here that it's happening in our sun, and it happens in any star that first begins. Now, there's other levels of fusion. As you'll see, if you watch that video that I posted about neutron stars, it has a great summary of how stars work. They actually fuse elements all the way up to iron. I realize that's only 26 elements, so there's a whole bunch of other elements that have to result from more combinations, which actually come from explosions that happen when the star explodes eventually, if you know that. But so anyway, you should be able to recognize these symbols. H, of course, is hydrogen, and and the He is helium. And the top number it's called the neutron number. You don't have to really remember that per se, but it's the nucleon number because it's the number of protons and neutrons. Okay, so in this case, this is a helium atom. You have two helium atoms. They have one proton and one neutron each, which gives them a total of two nucleons. A nucleon is just what's ever in the nucleus. Okay, so the I guess I could label that if that helps you. We call that the um, nucleons, which are protons and neutrons, the top number, and then the bottom number are protons. Okay, so you can see here in the process, both the top numbers and the bottom numbers balance. It's just like chemistry. I know some of you guys have taken physics, so you're really familiar with this. But see, on the top row, we have four nucleons at the beginning, and then afterwards we have four nucleons total. Sorry, I blocked those out. Okay, we have 3 plus 1. So we still have four nucleons at the end. And same with protons. We started with 1 plus 1 is 2 on the left, and then we have 2 on the right. And so in the process of fusion, two hydrogen atoms fuse and they become helium. And they also make one neutron. Okay, so that 110N at the end, that's a neutron. And then this guy here, of course, is helium. And it's helium number 3. There's a couple different isotopes if you're familiar with that term from chemistry. But this is the fusion process. So in simple terms, we take the simplest element in the universe, which is hydrogen, and we fuse it together to make helium. That process again is fusion. That's where you take two small nuclei and you make something big. And it releases energy. That's what's missing, I guess, from this equation, is it releases a whole bunch of energy, quite a bit per kilogram of mass. Okay. And all stars do this. Now, the opposite of that, which you should just know, is it's nuclear fission. Fission is splitting. Okay, and fission is that's what we typically think of the atomic bomb. It used nuclear energy from fission. Primarily, it was uranium. They also use plutonium. There's a bunch of elements that are unstable that will, on their own, or if you encourage them, they will split and they will release huge amounts of energy. Okay, so there you have it. There's fusion and fission. But really, fusion is the one you need to know the most because that's what stars do. Okay, that's how that's the reaction that's actually releasing energy, that's releasing all of this, highly charged particles and electromagnetic radiation. All that bit of energy is coming out. We're going to look at that right now. Now, um, as I noted here, the surface of the sun is not its hottest location. There's different layers of gas that have increasing temperature, and the electromagnetic radiation with higher and higher energies corresponds to higher and higher temperatures, because in order to make high energy photons, you need high temperatures. So I'm just going to kind of zoom in here a little bit. If you look at the surface of the sun, it's only 6,000 degrees Celsius. Note that we're getting visible light and infrared light, or visible photons and infrared photons come from just that surface. But then you go up to the first layer of atmosphere, that's 10,000 degrees Celsius, and that's where ultraviolet rays come from. And then so on and so on. So you can see we get higher temperatures. X-rays happen in the middle. This is the one worth noting. The sun experiences what are called solar flares. You've probably heard of that. It's kind of like the sun just belches out huge coronas. They call it a corona discharge sometimes too. But these solar flares are just a huge disruption of energy, of energized particles under really, really high temperature that releases all of these types of electromagnetic radiation. Now there is still, see, the upper atmosphere can still produce X-rays, but hey, the solar wind is all of these particles being thrown outwards from the sun in all directions, and that's what radiates outwards throughout our entire solar system. Okay, basically that the limits, like the energy does kind of dissipate, and eventually it runs out. And then when that happens, you're not part of the solar system. Basically, that's the definition of our solar system in terms of its limits. So you should know that the solar flares, they're the dangerous ones. They generate gamma radiation, and they are potentially disruptive to radio signals and other kinds of electromagnetic radiation that's on the Earth because they have such high energy. So just scrolling down, this picture shows what the atmosphere, the layers of gas around our Earth do when all this stuff comes to hit us. Okay, so all these white lines here are showing different kinds of electromagnetic radiation that's all coming from the sun. If you'll note here, the bottom says what's absorbed. So long wave radio waves are absorbed by the atmosphere. So you can see their white lines right here, they never make it to the Earth, okay? But what does make it to Earth are all of these guys. So the radio waves, there's some infrared that makes it, okay? And then definitely visible light and some UV, okay? So all of that's the type of energy that's making it to the Earth. We studied in the previous one, it's the ultraviolet, the third type. So it's ultraviolet C, UVC, okay? Or electromagnetic radiation that is blocked by ozone, okay? Now, and then of course, all these others are also blocked, thankfully. If we were being hit by these, we'd all have cancer and it'd be crazy. Our lifespans would be shortened dramatically, but so all of these further types of electromagnetic radiation are blocked by the atmosphere. And there are some solar wind particles that are also absorbed by the atmosphere. Northern lights are worth mentioning. These are just highly charged particles, usually protons, okay? But when they fly into our atmosphere, they excite the oxygen and the nitrogen that's already in it, and they cause it to produce light. And it's usually green, sometimes red if you're lucky. But that kind of shimmering northern lights, if you've never seen it, it's fantastic. Obviously easier to see the further north you go, but it's not impossible to see it here in Carson, which I have done in the past too. So I kind of summarized that already. It is worth noting as well that ozone isn't the only life-saving molecule out there. There's water vapor, methane, and carbon dioxide. All of those components in our atmosphere, they all absorb electromagnetic radiation. Obviously, you're familiar with the greenhouse effect. Those gases actually absorb that energy, and then they re-radiate it as infrared or as heat. And so too much of that has been increasing the overall temperatures of the Earth in the last decade or so, which is very alarming. But we're trying to manage that as best we can. So that leads us to some properties of light that you just need to know. There's lots of math behind all of them, but we don't need to know the math. You just need to know the basic principles. So there's 5 of them. Well, basically there's 4, but 2 of them are combined. So you need to understand reflection. I don't think reflection is too difficult. Here's a good picture of it. Basically, it means that the angle of incidence equals the angle of reflection. We do measure that to this red line, which is called a normal, but you don't need to necessarily know that too much. You just need to know that light, and not just visible light, but all forms of electromagnetic radiation can exhibit reflection. Okay, so you hit a plane mirror, it bounces off at the same angle. Refraction is the next one. Refraction is actually pretty cool. It is the result of the phenomenon that light travels slower in more dense mediums. Okay, we've already studied that light travels at 3 times 10 to the 8th meters per second. When light hits a more dense medium, it slows down. Now, this one shows it a little bit better. I'll try and zoom in on this. If light was coming in right here in this direction, going like this, okay, these little the dotted red lines show the wave fronts. Now, when the light waves hit the dense medium, like say this is glass or something, you're going from air to glass, we could say, okay, if you need a reference. So the idea, though, is that you can see right here, this part of the wave, you can see that part of the wave has hit the glass and is starting to slow down, whereas this part of the wave is still in air and it's still traveling at 3 times 10 to the 8th meters per second. So in glass, it's a little slower. It's not much slower, but it's slow enough that it actually bends and changes the wave. So now the wave fronts are moving away like this when they were coming in like this. Okay, so that is really, I'll just clear all that off so you can just see the picture. That is really what refraction is. It's the bending of light due to the fact that light travels at different speeds in different mediums. So Isaac Newton was famous for showing this with white light or with light from the sun, and he got a slit of that light to shine through a glass prism. And what he found, which was really cool, is that every color actually refracts at a different angle. So red, in fact, refracts the least. So here's red here, and then of course violet, which is really a dark blue. Sorry about the fact that it's purple. Roses are red, violets are blue. Not roses are red, violets are purple. So anyway, that's kind of a phenomenon. Purple is really the result of red and blue combined. Most of you understand that from just mixing colors. White light has no purple in it, okay? So anyway, but that's just kind of an error that creeps into a lot of these pictures. But that's refraction. So refraction is the bending of light due to it passing into a different medium. Now, there's another phenomenon that can actually produce a similar pattern to refraction, and that is something we call diffraction, okay? Basically, waves exhibit diffraction when they pass through a small opening, because when they do, they radiate outwards from that opening in all directions. So what that looks like is here. See, these are called apertures, kind of like if you know anything about photography, it's how wide the opening is that you're letting light through. So if you have a large aperture, anyway, a large aperture is a large opening. You can see these waves coming in right here, and they're not really changing too much after they get the opening. There's kind of a slight curve, as you see, but they more or less are continuing onwards, and they're not really radiating outwards very much like that, okay? Whereas if we get to a narrow opening over here, this is really showing diffraction, because if you will, part of the wave front, like this little part right here, just keeps going straight, okay? But the wave actually bends around the opening, and it makes what we call almost like concentric circles. So these are circles that share the same center, okay? And they just keep radiating outwards like that. And this is a wave phenomenon. So all waves exhibit this: sound waves, light waves, any wave you can come up with will exhibit this property called diffraction. And what's neat though is if you get two openings. Okay, so this is just one opening. If you get two, I'm just going to jump down here. Two openings or narrow slits, they will cause two sources of diffraction, and then they interfere with each other. Then you get waves overlapping waves. And I mean, if you can imagine in a swimming pool, you drop two rocks in the swimming pool and they both start making ripples. Those ripples would overlap and they would form a pattern that looks just like this right there. Okay, now if you have a screen or a detection device at a certain distance away from these slits, then you're going to have areas where when they hit the screen, there's areas where the crests from one wave meet up with the crests from another wave. And when you get two crests meeting up together, then they add together and they form like a super wave, or they call it superposition, which some of you may be familiar with that term. Okay, so what you'll do is you'll have areas of, if it's light now, you'll have areas of brightness and you'll have areas of darkness. And brightness is called constructive interference, and areas of darkness is called destructive interference. Okay, so that's why I put these terms together. Diffraction and interference are very closely related, because if you can observe diffraction like you see here in this picture, you will get interference as well. And those are two classic properties of waves, okay? Diffraction and interference. I did add this note here. It wasn't in your notes originally. Um, Actually, Thomas Young was the first guy to figure out that you could do with two slits, you could make this pattern. And really quickly after him, they're like, man, well, what if we made a whole bunch of slits? Then we should be able to define this pattern even better. And that's exactly what happens. But if you get a whole bunch of slits close to each other, that's called a diffraction grating. And you'll hear me use that term a little bit later too. But the diffraction grating, you can make them by scratching glass. So putting etching marks on glass really, really close together. Like we can have machines do it, and they can put, hundreds and hundreds of scratches per millimeter of distance to create diffraction patterns that are easy to reveal the interference patterns for light. Okay, so for the slits to work, they have to be close to the size of the wavelengths. And that's kind of what this is showing here. So see, this gap here is pretty close to the wavelength, okay, the distances between each crest. So, but that's diffraction and interference. Now, the last one, basically this is the fifth one, but if you put diffraction and interference together, there's just four. Polarization. Waves also can be polarized, is what we can say. And it's the process of polarization. Light waves, they actually vibrate in all directions. So you get like, the changing electric field and the changing magnetic field that we learned in the other section. That happens in all directions. And that's what's being shown right here, is that the waves are vibrating in all directions, okay? An unpolarized incident beam. But if you put up a polarizing filter, and those can be crystals or a certain coating where there's a vertical or horizontal alignment with the structures inside, you can block all of the wavelengths of light that aren't going vertical. Okay. Now, after the polarizing filter number one, you'll see that there's only the vertical there's only the wavelengths that are going up and down that made it through that, okay? And then you can classically do, in fact, I wish I had my filters with me. I could show you that you can cause the filters to, you put them perpendicular to each other, you can actually block out all the light, because see, the second polarizing filter could block it out completely. I like showing this picture as well. In the Inuit in the north here in Canada, for years they understood how dangerous it is to be out on the ice and snow when the sun is out and there's no cloud cover. You'd experience what's called snow blindness. There's so much reflected light entering your eyes that it gives you a crazy headache, and it can seriously make you sick. So to combat that, they take whalebone and they just cut slits into it. And what that does is it blocks out all the light except for the light that's vibrating in that plane. And it's a really clever um, trick to cut down the amount of sunlight that's entering your eyes. And basically, as you probably all know, almost every set of sunglasses you buy these days has the capacity it has polarized filters. In fact, it'll even filter out ultraviolet light. A lot of them, if you get different kinds, but they'll usually say polarized lenses or ultraviolet protection or something like that, which is really, really good because it minimizes the amount of sunlight and ultraviolet too that could be penetrating your eyes. So those understanding those principles led to the invention of the telescope. As soon as we learned that you could bend light and direct it and focus it, then you can create images. And Galileo was the first one to invent a telescope. He used two lenses. What I want you to be able to see, if you saw a picture of a telescope, you could tell me what kind of a telescope it is. If it's using lenses, it's known as a refracting telescope, okay? Because it's bending the light, okay, causing it to change direction. And actually, Galileo is using two types of lenses. This here is a diverging lens, and this is a converging lens. But you don't really need to know the difference between those for this. Johannes Kepler did one as well, but again, he's using a lens. So you're looking at, if you look at the telescope, it's using lenses. So yeah, those are refracting telescopes. Isaac Newton was kind of the first to realize that we could collect a lot more light if we used mirrors. There are limits to using lenses. You can only make lenses that are so big. Too much a glass that's too thick can basically distort the image and make it unclear. And also large lenses are hard to make. But Newton realized you could use a curved mirror like this one. So, and what's awesome about using mirrors, you can make them as big as you want. So sure, he's still using a lens here to kind of focus the light right at the end to get it to go to your eye. But using a big curved mirror here, he's also using a flat mirror just to kind of control the light. That you can see objects that are even further and further away. And yeah, I need to post a video about different telescopes because we use telescopes of all kinds to see every part of the electromagnetic spectrum. The most famous telescope probably is the Hubble Space Telescope. It was launched in the 90s. They had some difficulties with it, but it's been working fantastic ever since they fixed it. And it has produced some of the most just mind-blowing pictures of space and really helped us understand the nature of the universe. So with any given telescope, though, there's an issue here with what's called resolution. And I'm not going to read all of this because I think you guys can get a minute, you can follow that. But if the ability of a telescope to distinguish the fine details of an object or collection of object is called the resolution. So a low resolution telescope, you can only see large features. You can't differentiate between two objects that are close together, especially if you're looking at stars. Like if you had two stars that are really close together, if you had a low resolution telescope, you would look at it and you'd think it's just one star. A high resolution telescope allows you to see details between two close objects. So there, a viewer could distinguish between two stars that were close together. So here's a picture that kind of shows that. If you have a large opening here on the left, you can see that these two light sources come in and you can easily distinguish two objects. But objects passing through small openings, diffraction is going to happen. If you can zoom in here on this, you can see that there's these concentric circles forming. We have some interference happening. And if they're too close together, then the resolution here would not be great, and you couldn't tell that there were two objects. So this is definitely a problem when we're looking into space. So something that we have to address. Now, uh, something else that's really neat about studying space is because we can study every aspect of the electromagnetic spectrum, um, there's a trick that we use to visualize it, and that's called false color imaging. You may have heard of it. It's where we take unseeable electromagnetic radiation and we convert that into a visual image so that we can emphasize the location of this kind of electromagnetic radiation and even the intensity, how strong it is in different parts. So this here, these are 6 pictures of the exact same part of space. Okay, and I'll maybe scroll up so you can see these. Um, the This is called the Crab Nebula. It has some funny names. But this, the very first one here, this is radio waves. Now you can't see radio waves. Your eye can't detect those, but we can detect them using radio dishes or radio telescopes, they're called, and we can generate an image that a computer can then convert into something visual that you can see. And yes, we just use color, we just add color afterwards because radio waves don't have a visual color, right? So in moving onward, this one is infrared. So this is an image made from infrared wavelengths. This picture is visible light. So this is what it would look like to, say, the Hubble Space Telescope, which I'm sure is the one that took the visible picture. And then, of course, we carry on. So an ultraviolet detector would have produced this picture, and then it was converted using false color imaging. And this one, oh, X-ray, this one's fascinating too. See, look at that. You can see in here, you can see here that there's some concentric circles radiating outwards. That could mean, obviously there could have been an explosion here of a star of some kind, and it's over time, it's just moving outwards from the point of explosion. But that's not obvious in any of the other spectrums, which is kind of cool. And then the very last one here is just all of them combined. So it says a false color composition of all of them put together. And yeah, I mean, we can learn a whole bunch of stuff by probing the universe in these different wavelengths of the electromagnetic spectrum. So all that combined is an example of the next term. It's really called multi-wavelength astronomy. And this is where astronomy has evolved to, because we have the capacity to study all of the wavelengths from radio, which is super big, like hundreds of kilometers in their wavelength, all the way down to X-ray and gamma, which are ridiculously small, times 10 to the negative 10 and negative 12 meters. Very, very small. So then that tells us a whole bunch of stuff about the stars, about what they're doing, how much energy they have, what's going on, and it's helped us really understand how they work. So worth mentioning is studying the radio waves, which are the biggest ones, like I said. Because they're so big, we have to use machines like this. And you've probably seen pictures of these in lots of movies, because to probe deep space, we can look for radio waves coming from stars that are, light years away from us. But to do that, you have to be able to detect really long wavelengths. So you can't really tell to scale. Like right there is a little building, and there's a road there, like a railroad track that all these guys are on. These dishes can be like 20 or 30 meters across or something like that, and they're arranged in what's called a very large array, which usually it's a Y shape, but there's other configurations you can stick them in. The point is that they all will pick up pieces of a radio wave. Okay, so if every single one picks up, you might have one big wavelength, something like this, and every single dish picks up a piece of that wave, and it's the same wave, but you need all that space to detect just one wavelength. And so doing that, then the computer can stitch that all together and start to make an image. It's a very fascinating process. It's very technical, but possible because of technology, that we can actually detect radio waves from crazy deep parts of space. Now, we can study every other aspect too. I mean, we study microwaves. We use telescopes that detect microwaves, detect infrared, as you see in this multi-wavelength astronomy pictures. Absolutely fascinating. Okay, now there's another aspect that we can learn from studying visible light now that comes from stars. And what we do is you take light from a star and you pass it through what's called a diffraction grating, which we've already discussed, or you can pass it through a prism. And when you do, actually, that's what these two are contrasting here. If you look here, this one right here. This is showing, actually, it's a burning candle. But if you generate light and you pass it through a prism, then the prism will bend that light into its different colors, which I'm showing you right here. Okay, different colors will refract at different angles, and sorry to jump around so much, but that will produce a spectrum. And so one method is to use a prism, which uses refraction to create this spectrum or range of colors. And the other one is just to use a diffraction grating. Spectroscopes are pretty simple. On this end right here, this is the diffraction grating part. Okay, so it's just a whole bunch of vertical slits in plastic. They're really, really close together. And then on this end over here, you'll just have an opening, like a single slit that will let light, so light will come through that, and then it'll hit the diffraction grating. And that diffraction grating with all of those slits will actually produce a spectrum, and it'll do it like this, okay? Like this one. So if you shine the light through it, it'll create the different colors will spread out on basically on the back of your eye, but if you could do it on a screen, it'll spread them out into different colors, very similar to this. It's actually the reverse of refraction, but you don't need to know that. It definitely spreads them out though into their different colors, okay? So we kind of have two ways to analyze light, but you need to know the three different kinds of spectrums, okay? So spectra, just a little bit of vocabulary, that's plural, and spectrum is singular. So white light, or light from a hot glowing solid, if you will, like heating up, in a forge, a piece of iron, you heat it up and it glows red. Red is the dominant color, but if you could take that light and shine it through a diffraction grating, you would get a continuous spectrum. It would be the entire visible spectrum. So from red all the way to deep blue, you would see all the colors. That's a continuous spectrum. Now, another way, though, is if you take an individual element in the gas form. So it says here a hot gas. So if you did heat up a gas, and that's easy to do if you run electricity through it, we can do it in a glass tube if you is an easy way to do it. That light, but you have to pass it through a diffraction grating in all cases. Then you create what's known as an emission spectrum or a bright line spectrum. And what's really neat here is this gas is only being excited at very specific wavelengths. And what's happening is electrons are getting excited and they're falling back down. There's kind of a cool process that happens here. But what you need to know is that every element has a distinct emission spectrum. It's just like a barcode, like those I don't know if they're called UPC barcodes or whatever, that are on every product that's scanned at the grocery store. Elements also have a very distinct barcode or a code of individual colors. And it's so cool that all the elements do that. Now the third one is a different way of identifying a metal, and that is you take white light again from a hot glowing solid, but you shine that through a cold gas. So this time the cold gas means it's unexcited, it's unenergized. But what'll happen is the continuous spectrum comes through, but it's missing some pieces. And those pieces are called black lines or dark lines, the dark line spectrum. Okay, so an absorption or dark line spectrum happens when you shine that white light through a cool gas. All the colors make it through except for those. So to show you, oh yeah, I already emphasized that. All elements have a distinct emission or absorption spectrum. So you can see here the continuous spectrum. Here's just a number of elements. Hydrogen, it's so cool if you can actually see this. And there's ways we can do it. if I heated up a tube full of hydrogen and you looked at it through a diffraction grating, now not just with your naked eye, because you don't have a diffraction grating in front of your eyeball, but put a diffraction grating in front of it, and you will only see like these, these little bits of purple, okay? And then, and then you'll see like a blue, and you'll see a green, and I think there was one other one. Yeah, there's a red. So you'd see just like one little strip of red, and that's it. Like you would literally see that in using the diffraction grating. And then you can see the pattern is different for everyone. There's sodium, helium, neon is a cool one. Obviously, there's a lot of red in neon. You see a neon sign, and the bulk of the colors you can see are red, but you wouldn't know unless you had a diffraction grating. There's actually a little bit of yellow. Okay, there's a little bit of yellow in neon, but essentially no other color in that. So uh, scientists were really excited once they figured this out, because it meant they could look at the light coming from a star, like a distant star. You could look at that light, you could run it through a diffraction grating, and you could tell with certainty what elements were in that star. And that was mind-blowing. We weren't able to do that before. So we are able to learn things about stars that are super far away. We can tell what they're made of. So worth noting here is if you lined up a bright line spectrum with a dark line spectrum, or an emission spectrum with a absorption spectrum, they would line up. So you can see right here, this is Mercury. This first one here, this one here is the bright line spectrum, and then here's the absorption spectrum, and they line up. Okay, so the missing dark lines line up with the bright lines. Just confirms that, yeah, you got Mercury. So you need to be comfortable at least interpreting or understanding what spectrum are. So another property, which is, and there's a video of it that I posted as well, is the Doppler effect. Anytime an object that generates waves is moving, the waves will bunch up in front of the object as it moves, and the wavelengths will spread out behind it. The video does a great job of describing that. I think most of you guys are okay with that. This picture does a good job of showing that too. A stationary source, the wavelengths are all the same, but if the source is moving to the left, then the observer B here is going to have much larger wavelengths, okay? See that compared to this guy, because the source keeps moving to the left, and so the wavelengths bunch up in front. Now, we usually think of the Doppler effect with sound waves, which is the easiest way to understand it. But because light is also a wave, light waves do the same thing. And so you might remember this from your Science 9 classes. If a bright line or any spectrum, if it shifts towards the blue end, that means that the object is moving towards the observer. Okay, so blue wavelengths are really, really small. So if you're moving towards blue, you have a tendency to, everything tends to shift towards blue. But if that object is moving away from you, then you get what's called a red shift. So the red shift is where the wavelengths are actually getting farther and farther apart. And a red shift means that the object's moving away from you. As noted in the video, because essentially all stars and galaxies that we look at around us, all their light is red shifted, so it's shifted towards red. That means everything's expanding. That means that things are moving away from each other, and they're moving away from us, the observers, right? We're here on Earth trying to figure that out. So I want to just walk through this example for you. Here's a spectrum. Now, I don't have a key for you, so I don't know what element this is, but this, I would hope you could look at this and tell me, is this a continuous spectrum? Is it a bright line spectrum, or is it a dark line or absorption spectrum? So I'm hoping you'll see this as absorption for sure, okay? Because it's you kind of see all the colors, but there's missing dark lines in there. So we're going to say that this is our spectrum, and then it shows us a picture like this. So the next spectra were taken where the sources were moving with respect to the observer. So we have A and B. Now, what I want you to see here is that the pattern is the same. See, we have two that are close together here, and then you got two that are close together here, one and one, and so the pattern, like the spacing of the dark lines, is the same, but this one has shifted towards blue. Okay, so this one shifted towards blue, and this one has shifted towards red. And actually, let me show you the reference line here. So maybe I'll just erase this part right here, because what you need to see is, this is where my eye just kind of went to this line right here. Okay, so this would be kind of my reference line, and if I look for that same line in the next spectrum, well, it has shifted over this way. Okay, so there it is right there, like it's shifted over. And then in this bottom one, it has shifted to the left. Okay, so this one has shifted towards red. Okay, so all it's saying is, yeah, this is the same element, like maybe it's, I don't know, calcium or something, or whatever element this might be showing. It's just that in spectrum A, it has shifted. Everything just like moved over towards blue, and then in the other one, it shifted over towards red. So I guess what we should say that is A is moving towards us. Okay. And in B, it's a red shift, so that's moving away from us. And 22 is worth noting. It says, which one of these two spectra was produced by the faster moving source? So the greater the change, the greater the shift, the faster it must be moving. Okay. So based on that thought process, A is moving faster. Okay. It has definitely shifted more away from our baseline absorption spectrum that we started with. Okay, so that's what I mean by a blue shift and a red shift. So what's left? You just need to know generally how we classify stars, just to end. And there's a whole bunch of really cool science behind this. You just need to know it on a basic level. Stars can be sorted by their temperature, and they can also be sorted by their brightness or their luminosity. Okay, there's that word luminosity. So, and what's interesting here is we go from left to right. Actually, towards the right, these are cooler stars. Okay, you can see it's 2,500 K. I mean, that's not very cool, but it's ridiculously hot. But what's even hotter is over here. Okay, so as you remember, blue is the hottest color. If you make flame, if you're a welder or using an acetylene torch, a blue flame is hotter than a red flame or an orange flame. Same thing with stars. Okay, so yeah, the stars that are larger actually are the brightest, and that's what I summarized here. Brightness corresponds with how large the star is in most cases. Okay, so supergiants, those are the biggest stars. And if you look at this, as we come down this way, basically from top to bottom, we go supergiants to giants to the main sequence to white dwarfs. Okay, so white dwarfs are weakest in their luminosity, so they're not generating as much visible light, but the larger stars generate more. And this pattern here actually maps the evolution of a star, okay? At least the last part of it. Once stars become supergiants, actually they kind of don't go from supergiants to giants, but in general, though, you go from top to bottom in the evolution. So this is the last part you need to know just generally, and a lot of it is Science 9 space. So you can see here that this is where stars begin. They start in a nebula. Okay, it's a ball of gas and dust, and gravity pulls together huge clumps of it into balls of hydrogen. And as soon as that hydrogen starts to fuse together, they call that a protostar. It's like as soon as you can see light, then you know that fusion's happening. But depending on how much mass comes together, there's really three different branches, which one of the videos does a great job of defining with a lot of extra detail, but it's still really good. So They're calling this low to medium mass stars that include our sun that might go through this main sequence going this way. And then if a lot of mass comes together, then you would go this way. But the top route, you need to know that you could go from a nebula to like a main sequence or low to medium mass star. Over time, over millions and millions and millions of years, it will undergo fusion and grow bigger and bigger and bigger until it gets to its maximum size. And then, as you may have noted in that video, the radiation pressure in a star is always acting outwards, but gravity is trying to pull it together. And as long as those forces are in balance, the star is in balance. But as the star evolves, the nuclear forces get weaker, okay? Because it runs out of fuel, it runs out of hydrogen to keep fusing, and all the other elements too. And finally, it fuses until it can't fuse anymore. And when that happens, it has so much mass that gravity starts to win, and then the star collapses. The inner part of the star collapses on itself, and the outer parts get blown out in either a supernova, which is down here, or it's kind of just a nova. It's not super. The difference is presentation. No, that's the difference between a villain and a supervillain. Anyway, so but a planetary nebula is kind of this collapsing of a red giant, which then becomes a white dwarf. Okay, and you'll see that in the video too. Now, the other possible round is if it's much, much bigger, then you can get a red supergiant. This is a monster, okay? Betelgeuse is a red supergiant. If you know Betelgeuse, it's kind of the armpit of Orion, the constellation Orion. Huge, huge red supergiant. When those collapse, that's a supernova. And again, depending on how much mass, a high mass star would collapse to a neutron star in the end. That's what it would wind up being. And I did note off to the side, some neutron stars can be identified as pulsars because they spin so fast that they're generating a radio signal, which can be picked up very easily by those radio telescopes. So the neutron stars are insanely dense, but they are not the most dense particle in the universe. That is reserved for the black holes. And we call them black holes, but they're really not holes. They're really insanely dense matter that has gravitational field so strong that nothing can escape it. Okay, so matter nor electromagnetic radiation can escape. And they're super fascinating objects in space. The reigning theory is that every galaxy has a supermassive black hole at its core that's holding the whole galaxy together. Our sun is orbiting a supermassive black hole at the center of the Milky Way, which is our galaxy that we named it, right? So anyway, as the video notes, what really determines if you're going to get, these are the corpses of stars, right? Either you're going to end with a white dwarf, a neutron star, or a black hole. Those are your options at the end of a star's life. And which one you get depends on how much mass you started with. Okay. Anyway, so that's a compression of all that theory. I'll try and get some review stuff coming up because we've got a test coming up for the physics unit, but that basically covers astronomy. Keep it up, you guys.